Alright, this video is on the washer method for finding the revolution of, like when we revolved this around the x-axis, before they formed a solid, okay? And remember, because they formed all those little semicircles, that can be called the disk method. This is called the washer method because when you revolve this around, it's going to basically create a washer effect, okay? Or donut, if you want to look at it like that. Okay, it doesn't matter what you call it, but it's going to create this shape. The good thing is both of these will always be circles. So it's really easy to figure out what the area of the washer, so to speak, is. Okay, because if we revolve this around, it's going to be the outer. It's going to create an outer edge and an inner edge. Alright, so what you're going to do is you're going to integrate to find the outer edge, and you're going to subtract that from the inner edge. Okay, so we're going to find the whole thing, and then we're going to subtract out this circle in the middle. I'm going to black it out. We're going to subtract out the circle in the middle, so all we're left with is the washer. So if we look here, we have y equals x, and we have the graph y equals x squared, and we're going to be revolving it around the x-axis. So to find the area, we're going to have to subtract the outer edge from the inner edge. Well, the outer edge here is going to be the graph that's on top. All right, our graph that's on top here is y equals x. And of course, we're going to integrate from 0 to where they cross. Well, we know they cross at 1. So we're going to integrate from 0 to 1 pi x squared dx. Okay, remember this is what we did before. But this is going to give us this whole triangle here spun around, so it's going to give us a cone. But and of course all the cross sections are circles, but we don't want that. So from that we're going to have to subtract our inner edge. All right, a to b will always be the same for both of them. Pi times, and of course our inner edge is y equals x squared because it's the graph on the bottom, squared dx, okay? So you could pull out the pi, integrate both of these. I'm going to do it up here. And when you integrate them, you're going to get pi times x cubed over cubed, evaluated from 0 to 1, minus pi times x to the 5th over 5, evaluated from 0 to 1. Of course, in these examples, the zeros will cancel out. You won't even have to worry about them, so it's just evaluated at 1 minus evaluated at 1. But when you plug in a 1, you're going to get pi over 3 minus pi over 5. Bump them up to a common denominator. Of course, your common denominator is 15. And when you subtract that, you are going to get 2 pi over 15, okay? Because of course you're going to multiply this one by 5, so this is 5 pi over 15 minus, multiply this by 3 pi over 15, which is 2 pi over 15, okay? So if you were to rotate this around the x-axis, the resulting washer would have an area of 2 pi divided by 15. Alright, now just like for the disk method, you can also revolve around the y-axis as well. The only difference is you got to solve your equations for y. So let's use the same two. We know they cross at 1, 1. This is y equals x squared. This is y equals x. We're finding this. But now we're revolving it around the y-axis. All right? So you still do the same thing, except of course now we have to solve it for y. All right? Well, we know when we evaluated our integral from 0 to whatever, well, since x and y are 1 where they meet, we're still going to evaluate from 0 to 1. All right? So we're still going to do the same integral. Of course, we have to have pi in there because we're creating circles. But now we have to figure out which one's on top, which one's on bottom, subtract the two, and get our answer. Okay, when we're revolving this around the y-axis, the one that appears to be on top is y equals x squared. An easier way to tell this, because when you're revolving around the y, it's not really on top or bottom. It's whichever one is the furthest from the axis. And that description will actually work for both of them, revolving around the x or the y. But it's the one that's going to be furthest from the axis. So the one that's going to be on top is the y equals x squared. But of course we have to solve that for y. Solve it for x. So take square root of both sides. X equals the square root of y. Okay, so this is going to be the square root of y squared dy minus, when you solve this for y, hey look, it's already solved. X equals y. So this one's just going to be y squared dy. So squared cancels that out. So this is going to be an integral from 0 to 1 of pi times y dy minus 0 to pi times y squared dy. So when you integrate them, this one's going to give you pi times y squared over 2, evaluated from 0 to 1. I don't know why I put a pi there. 1 minus, this one's going to be pi times y cubed over 3, evaluated from 0 to 1. Again, the zeros are going to pretty much cancel out, so you sub in a 1. It's going to be pi over 2 minus pi over 3, which leaves you with pi over 6. So our resulting washer, as you spin this around the y-axis instead of the x, as you spin it around the y, it is going to give you an area of pi over 6. Alright? So I could keep giving you examples, but that would just be monotonous, because they all work the same. You already know how to take the integral to find the solid that it makes. So now all you're doing is subtracting the smaller solid from the bigger solid. Your inner subtracted, you take your inner and you subtract it from your outer. Alright? So it works the same way. Now you're just doing two integrals and subtracting the two. Alright? So make sure you understand, this is called the washer method. Make sure you understand the washer method for when you come to class tomorrow. We're going to be working on some problems on this. So see you tomorrow.